Okay, it seems that we are live. Okay, so hello everyone and welcome back to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar 104, and we are having Andres Florez as a speaker. Andres carried out his PhD at Vanderbilt University, which was followed by postdocs at York University in Canada and the Universidad de los Andes in Colombia. He then got a position at this university, at the Universidad de los Andes, and now he's an associate professor there. Today, Andres will give us an update of new physics searches using the Vector Boson Fusion process. So we are tremendously happy to have him as a speaker today. So before we begin, as usual, I'd like to remind everyone that you can ask questions and make comments on the YouTube live chat system, which should be on your right. And these questions and comments will be passed on to Andres at the end of the talk. Okay, so without any more from me, I'll pass you on to Andres.
Hey, hi everybody. So greetings from Bogota, Colombia. Thanks for joining. Please allow me to share my screen. Let's see here. Let's see, this should be enough. Okay, let's see, let's share. So are you seeing my slides right now? Just wanted to be sure. Okay, thank you very much. And how do I minimize this? Okay. So I'm going to be talking about Vector Boson Fusion, trying to convince you that it's a very nice, complementary, and powerful tool to search for new physics at the LHC. Let's go to the next slide then. So let's start with some generalities of the standard model. As you all know, the standard model summarizes our understanding of fundamental particles and their interactions. It has been a very successful model that has been built upon experimental and theoretical basis. Nevertheless, we know that it is not complete. It has several open questions and some issues. So we have, for example, the hierarchy problem, where we don't know why the weak force, for example, is 10 to the 32 times stronger than gravity. So we have relative corrections to the Higgs mass that are of the order of the Planck mass, 10 to the 19 GeV. This is a huge issue, so we don't know how to eliminate those divergences. So gravity, you know, that is not incorporated in the standard model, so we cannot account for the neutrino masses. We know that neutrino oscillations imply they have mass. So we cannot also have like a suitable dark matter candidate that explains, for example, dark matter that if we believe all the astronomical evidence, so it accounts for 27% of the energy content of the universe. So in order to answer some of these questions, so we have the Large Hadron Collider, or we hope that through this experiment, so with this particle accelerator, we will be able to address a lot of these questions. So this cyclotron basically has 27 perimeter around basically a ring, and we know that it is located on the French-Swiss border, roughly 100 meters underground. So we have four main experiments. We have LHCb, Atlas, ALICE, and CMS. Nevertheless, there are other three small experiments that also, you know, have some very particular physics interests. I'm going to be focusing on this talk on one of these experiments, which is called CMS, the compact muon solenoid, which I also refer as the constant mental stress experiment. So this is one of the two largest detectors of the LHC, and it's a multi-purpose experiment. So I'm going to focus on the proton-proton collision program of CMS, where we collide protons at the speed that is nearly the speed of light. Out of these collisions, so from the vacuum, particles emerge, and we try to study the quantum characteristics of these particles in order to see if there is physics beyond the standard model that could explain some of the problems I outlined before. So the beam structure is as follows. Basically, we have bunches of protons that are being accelerated in opposite directions into different tubes inside the ring. And we have of the order of 10 to the 11th protons per bunch. And simultaneously, we have 2,800 bunches circulating at the LHC, and they collide at the center, geometric center of the detectors. And then we have the particles that we want to analyze after the collision. So this is basically the idea behind the LHC. So it has a design energy where we were expecting to collide the protons at the center of momentum energy of 14 TeV. Nevertheless, so currently we have reached 13 TeV energy, but we expect and we hope that for the high luminosity LHC, we will be able to reach the designed luminosity or the design collision energy. All right, so this is the CMS detector, and the basic concept behind this detector is the following. So here is the beam pipe, and we have a set of detectors that is surrounding this beam pipe. As I said, the protons collide in the geometric center of the detector, and then we analyze the particles that emerge from such collision. So we have, for example, a tracking system that is designed to reconstruct the primary and secondary vertices of some particles that decay, very promptly inside the detector volume. Then we have a silicon strip tracker detector that measures the trajectory of charged particles. Following this tracking system, we have an electromagnetic calorimeter that is made of some crystals that are made of tungsten lead material, and this material is very sensitive to electromagnetic interactions. So with this calorimeter, then we measure the energy of particles such as electrons and photons. Then after this electromagnetic calorimeter, we have the hadronic calorimeter, which allows to measure the energy of particles that have strong interactions. So we have very dense nuclei, and then particles, for example, like mesons, charged mesons or pions, for example, stop there so we can measure their energy. Surrounding all of this tracking and calorimeter system, we have a superconducting magnetic solenoid that is made of an alloy of titanium niobium. And this superconducting magnetic solenoid forms or generates a magnetic field that is quite uniform. It has a value of 3.8 teslas inside the solenoid, which is roughly 100,000 times the magnetic field of Earth. And then outside generates a magnetic field of 2 teslas. Outside this solenoid, so we have 3 different technologies to detect muons. We have drift tubes in the center part of the detectors, and in the end caps of the detector, we have RPCs, resistive plate chambers, and another set of detectors that are called cathode strip chambers. So the idea is that we have good and fast responses with some detectors, and with others we have very good position resolution. So with this in mind, then we can reconstruct different type of particles, for example, muons, electrons, charged hadrons, neutral hadrons, photons, etc. So for example, here we have an electron that bends due to the magnetic field, and with this bending we can measure its momentum. So it leaves a signature in the tracking system and then deposits the energy in the electromagnetic calorimeter. For example, a photon will not have a trajectory in the tracking system, but only an energy deposition in the electromagnetic calorimeter. So look at what we call a neutral hadron will deposit its energy. The hadronic calorimeter, a muon will transverse the whole detector. Basically, we'll see a trajectory inside the tracking system, and then we will see hits, what we call hits, in order to identify the trajectory in the outer part of the detector. So keep in mind that the magnetic field lines change because this is they change the direction because this is a magnetic solenoid. So that's why it bends in the opposite direction, the muon, in the outer part of the detector. Okay. So some important concepts so you can understand this talk is what we meant by cross-section in experimental particle physics. So basically, we understand this as a probability of production of a specific process. So this quantity basically is related with the level of interaction between either a beam and a target or between 2 beams. So in this case, we're going to focus on the production cross-section specifically, for a particle collider such as the LHC. The luminosity is a quantity that allows us to understand the performance of the accelerator. Basically, the number of events that come out of the accelerator are measured through this quantity that is called luminosity. It depends on the number of protons per in each bunch. This is the NA and NB parameters. Also the frequency of the collision that are the LHC. So we're colliding the protons every 25 nanoseconds. So we have 40 million collisions per second. So it's a huge amount of information. So we have a form factor that determines the angle at which the different bunches cross. And then we have basically also a dependence on the cross section of the particle beams. So once we collect luminosity throughout time, so we integrate then, and this is what we call the integrated luminosity. Another interesting quantity is the pseudo rapidity, which basically is related with the polar angle. We don't use the polar angle in experimental particle physics since it is not a Lorentz invariant quantity, but the change in pseudo rapidity, it is a Lorentz invariant quantity. Another feature is basically the dependence on the tangent theta generates a very nice feature where basically the particle multiplicity across the detector is quite uniform. You cannot achieve this with theta since you have basically a very different distribution of particles in the encamps with respect to the center of the detector. The missing transverse momentum is a very interesting concept that allows us to measure the presence of particles that don't leave signature in the detector. For example, we can measure neutrinos, or we can measure the presence of dark matter particles. So, and it's based upon the conservation of momentum on the transverse plane of the detector. Initially, the transverse momentum of the protons is basically 0. After the collision, particles emerge, and what you will expect in an ideal world is that the final momentum, transverse momentum left from these particles in the detector will be also equal to 0 because momentum must be conserved. Nevertheless, there are particles that you can detect in your detector, and there are particles that you cannot detect. These are referred as visible and invisible particles. The particles you cannot detect are, as I mentioned, neutrinos and perhaps dark matter particles. Therefore, this missing transverse momentum is defined as the negative sum of the negative vectorial sum of the transverse momentum of the particles you can detect in the detector. If we could measure everything, but basically this should balance out to 0, but it doesn't. Then when it doesn't, so you have essentially an indirect evidence of particles that did not were measured by the detector, and therefore they could be dark matter candidates or neutrinos, as I mentioned before. All right, so now let's go to the concept of a jet. A jet in particle physics, we could have 3 definitions. We could have parton jets, particle jets, and detector jets. A parton jet is basically a quark or a gluon, but we know that through the color potential, these, for example, gluons can generate quark-antiquark pairs that then, will separate, and out of this energy, the energy increases with the separation, so you can have particles that essentially pop up out of the vacuum, basically quarks and antiquarks that will form, for example, charged pions, chaos, or neutral chaos, neutron pions, etc. Once these particles that have emerged from these color interactions reach the detector, they will leave signatures, and this is what we call a detector jet. And we reconstruct this type of signatures that are color-mediated processes, basically using comb-based algorithms. So that's the basic idea of a detector jet. All right, so then what do we search for? How we do it? So depending on the signal model, we search for different combinations of leptons, photons, jets, B-jets, etc. So we use also the characteristics of the topology of the event to determine, for example, observables as the missing ET. We also use the topological features, angles, and so on and so forth to define other possible observables that could help us discriminate new physics from standard model physics. So, for example, we have the HT, which is defined as the scalar sum of the PT of the jets associated in the event. Therefore, so we have these handles. We have muons, we have taus, we have electrons, we have photons. We could have 0 jets, n number of jets, 0 B jets, jets that are associated with the big quark, or a number of jets in the physics we're searching for. We can have missing ET or HT or other variables depending on the topology of the event. So then what do we do? As a general rule of thumb, so we basically search for an enhancement of events with respect to the standard model background in a given distribution in order to search for new physics. If there is agreement between the background and the expectations, if there is no such enhancement of events, then we set limits at 95 100% confidence level on the production cross-section of such models. So in order to basically rule out the existence of new physics for these models and then move on and keep searching for new physics using other models. For example, we could have analysis that have 2 leptons in the final state, a number of bjets. You can require 0 bjets, the missing ET, and perhaps search for new physics using the HT. There are other searches where you basically veto the presence of any lepton or any photon in the event. You don't require nothing in the bjets, but you require just a number of bjets and missing ET. This could be, for example, a monojet search or even a BBF only missing ET search on the detector. You are searching for dark matter and you use the jets only to trigger and to target this type of physics and probe this type of physics in your detector. All right, so let's start then with one of very famous model is the model of supersymmetry. Supersymmetry is very interesting and very appealing, and it's a simple idea. It restores the symmetry between fermionic matter fields and bosonic force carriers, proposing this idea that there could be a new set of particles that could be higher energies, where basically matter is made out of bosons and the interactions are mediated by fermions. So this restores the symmetries between matter and force fields. With this simple idea, we can basically solve a lot of the open equations of the standard model. It has been shown that supersymmetry unifies the 3 included interactions in the standard model at a very large energy scale. Also, if you consider our priority conservation, there is naturally dark matter candidate, a particle that is heavy, is stable, and basically could has the properties to explain dark matter. So that being said, you know, we have an extensive search program for supersymmetry, and we haven't found it yet, but we keep looking because the open parameter space of SUSY is quite broad. So we need to basically be patient, analyze the data, and keep looking, basically. That's the whole idea. Initially at the LHC, so the color searches were quite appealing because the cross sections with respect to electroweave-mediated processes in supersymmetry were a lot higher. You know, we can talk about roughly 1 order of magnitude higher, you know, depending on the mass. But the idea is that a lot of focus was placed initially at the LHC of the searches. Nevertheless, since we haven't found, you know, signs of SUSY, so electroweave searches start to become more and more appealing. And what is very interesting is that although cross sections are smaller, also the backgrounds associated with the analysis are significantly smaller. And then these searches are quite competitive and complementary with respect to the color searches. So I'm going to be focusing on this talk on basically searches for supersymmetry in the electroweave sector. This plot is one of the CMS plots that summarizes many searches that have been conducted at CMS looking for neutrinos or for charginos that are going to refer as electroweakinos. So these limits, experimental limits, have to be considered or taken with very careful view on the physics, because they are highly dependent on the conditions of the model. What I want to point your attention to is that this part, basically this part of the phase space, most of the searches that have been considered have not been able to reach this aspect of the phase space. And this is what we call the compressed mass spectra scenario, where basically the mass difference between the dark matter candidate, for example, and the chargino, or the dark matter candidate and the S leptons, the supersymmetric associated particles to the leptons, is quite small. And this is a very difficult region to search experimentally. But to me, according to my view, is one of the best motivated regions to search for supersymmetry. Why? Because it has a deep connection with the relic dark matter density and cosmology. So here we have our Boltzmann equation, which depends on the average velocity cross-section. And the question is, how do we get a cross-section that in supersymmetry that is consistent with the cosmological observation? Studies has been performed, you know, and it has been suggested that if you only consider the main process, which is neutrino annihilation, in order to get a cross-section that gives you the correct relic dark matter density, the cross-section in supersymmetry is too high. Also, this cross-section will depend on the composition. This is the composition matrix of the neutrino, and it will depend if the neutrino is Vino, Higgsino, or Guino. The thing is that in order to lower this cross-section, you need to consider a process that is called co-annihilation between, for example, the S tau and the neutrino. If they are very close in mass, this process is allowed by, because of the uncertainties, is allowed in high energy physics. So these two can annihilate, and this will give you a relic dark matter density that is consistent with cosmology. So the general concept, and we know that the thermal dark matter models for dark matter. So here we have the co-moving number density, and basically the idea is that as the universe was cooling down, so it reached a point where dark matter became quite stable because there were processes like dark matter annihilation that were less likely to happen, and standard model particles did not have enough energy anymore to be able to annihilate and produce dark matter particles. Then the density becomes constant. But you could be in scenarios if, for example, we detect dark matter at CMS, Atlas, or other experiment where you can agree or disagree, depending on the cross-section and the characteristics of what you measure with respect to the cosmological observation. So in order to agree, then if we consider supersymmetry, we need annihilation, and we need to consider the mixing of the neutrinos. So in order to probe this very difficult part of the phase space, because the decay products that you can measure are quite soft, we have become very fond of this vector boson fusion technique. So the vector boson fusion technique experimentally basically is characterized by the presence of two highly energetic jets with a large delta eta gap that are located in opposite hemispheres of the detector. So these jets allow me to reduce the background events and allow me to target basically the events that using the jets, and it let me have three parameters here in the central part to detect muons that are or taus, or for example, or just trigger vicinity, and I can target leptons that are quite soft, quite low momentum, right? With that in mind, then I can target the compressed mass spectra where I expect the decay products, the leptons, to be low energetic, what we refer as soft. With this in mind, then let me show you some distributions in simulation that shows the features, the kinematic features of BBF. The black dots represent basically a BBF process in supersymmetry, and the red and the blue some background processes. So you can see that the BBF processes have a large reconstructed jet mass. Here, this is the eta distribution, and you can see that most of the events will end up in opposite hemispheres, so it has a very large pseudo-rapidity difference with respect to standard model backgrounds where these processes are more central. So we also have very energetic jets, and we have sizable vicinity due to the associated production of neutrinos, which are the dark matter candidates in the event. All right, so we started then in 2015 with this paper that was published using a center of mass energy of ATV. Oh, sorry. Okay, no, I have to go back. Okay, so here, this search considered initially basically the presence of two leptons in the central part, the two BBF jets. And with this idea, so we explored several channels, and with this idea in mind, we show now that we could probe the compressed mass spectra scenario. So we had a handle to start, looking in a region of the phase space that no other analysis had sensitivity before. And then we got very excited, and when you get excited, so you want to do more, and that's what we did. Basically, now we also explored another search that was published in 2017 at PRL that was basically aiming to search for supersymmetry also with the BBF topology, considering only vicinity in the central part of the detector. And then we place bounds on very compressed scenarios with S-bottoms, and also we place bounds using an effective field theory approach where we remain agnostic of to what happened in the center of the interaction, and basically we set a limit on the production of a dark matter particle, on this effective field theory approach. Of course, considering the energy scale of the theory, the corresponding truncation, considering the mediators, and so on and so forth. Everything was properly done from the theoretical part as well, and we placed very nice bounds on this type of production. So another search that was actually published last year, 2019. So now we realized that, okay, if we review the search with leptons, instead of requiring two, we realized that we could obtain better sensitivity experimentally if we consider only one lepton. There could be more leptons, but if these leptons are too soft to be detected, we at least wanted to probe events with at least one very soft lepton. And this showed that we could have even higher power to probe the compressed mass spectral region. So we use 4 final states with single muon, single electron, single tau, and also what we call the invisible, that is just missing a T in the central part of the detector. We combine all of these searches and we got this beautiful plot. In blue, what you have is the exclusion limit, basically that was placed by a very soft lepton analysis that didn't consider BBF, but more standard Drell-Yan production. And the green band corresponds to BBF. So these limits were set as function of the mass difference between the neutralino 2 and the neutralino 1. And here you have degenerate scenario where the Chargaino mass is equal to the neutralino 2 mass. What I want to point out is look that now we were able to place some bonds for delta times events of 1 GeV all the way up to 50 GeV. And here are the LEP bounds. So we showed that with this technique, we had a very, very good sensitivity to probe very compressed mass spectral regions. And as I said, the motivation is because only considering these compressed mass spectra, you can explain the dark matter relic density in thermal dark matter models considering supersymmetry. All right, now let me switch gears and I'm going to talk about some phenomenological studies we have been performing. So far, the LHC searches on Atlas and CMS have mainly considered the neutralino to be Bino or to be Wino. Nevertheless, now the Higgsino component is also possible. You can also have Higgsino dark matter. And for our surprise, what we found is basically that these Higgsino mechanisms come mainly from WW fusion, and this has a very nice enhancement of the forward topology of the jets. So for the Higgsino, for the Wino-Vino, the jets were not as forward as for the Higgsino case. And this is because basically this is coming mainly from a T channel rather than an S channel in the central part of the diagram. So the jets being more forward, so then you can have a stronger constraint on the delta eta. And then we're showing that this analysis for Higgsino is quite competitive actually with respect to other standard searches. So we have shown the signal significance. This is what these colors mean. This dotted line means the 5 sigma discovery counter. This is the 3 sigma discovery counter. And this is basically if we don't find, any sign of Higgsino's, what will be the 95% confidence level exclusion. We consider 2 channels, a channel with 2 leptons and a channel with 1 lepton, and we here combine them and we can see basically the change in sensitivity combining the 2 searches. So this phenomenological paper will be published hopefully this year. We are at the very end of the review process of the paper. So hopefully you're gonna see the complete story on the paper very soon at JHEP. All right, now, so another phenomenological idea that we proposed with my collaborators was to study the production of heavy neutrinos using vector boson fusion. Now we go from the SUSY world to other models, heavy neutrinos, set primes, anapole dark matter, gravitons, so on and so forth. So as you know, one of the open questions the standard model fails to address is the non-zero mass of the 3 generations of neutrinos. You know that there are the so-called seesaw mechanisms that propose, this possible heavy neutrino that could be of right-handed helicity. So if neutrinos, we know that the helicoidal symmetry of the standard model is broken. So if we find this presence, these heavy neutrinos with right-handed helicity, we will restore the helicoidal symmetry of the standard model. And also in models where these heavy neutrinos are stable, so they are naturally dark matter candidates. So we can explain also dark matter candidates through these so-called left-right standard model extensions. So then what is the idea? So we propose this BBF technique with 2 aims. First, so we need to get every single handle we can before the searches only consider the Drell-Yan production. But the problem with the Drell-Yan production is that we don't know how these heavy neutrinos couple to the color sector. We can have scenarios where the coupling is quite small, or even, we can have a color phobic scenario. And then the only handle you have to probe these heavy neutrinos could be BBF. And the other interesting feature we show with this paper is basically that people believe that the BBF cross-section was always smaller with respect to the Drell-Yan production cross-section. And this is not actually the case. There are some collinear enhancements that have been shown in some theoretical papers that make at some scenarios, some points in mass, BBF cross-sections larger with respect to Drell-Yan cross-sections. And this is what is shown in this plot, that after 1400 GeV, then the BBF cross-section becomes dominant over the Drell-Yan production cross-section. So we could have larger cross-section. We can probe different scenarios, for to target different couplings of the heavy neutrinos, and we are doing a complementary search to those searches from the Drell-Yan standard production mechanisms. So we performed the whole phenomenological analysis. We performed all the simulations. We came up with all of the Bayesian selection criteria that will maximize the possible potential discovery. And then we target the production with two channels, the channels with muons and channel with taus in the final state. And then doing that, basically, we again establish what will be the expected signal significance as function of the heavy neutrino mass for a 5 sigma, 3 sigma, and 1.69 sigma discovery potential. So this is for the muon channel, this is for the tau channel, and this is basically for the combination of the two channels. We also studied the mixing of these heavy neutrinos with the standard model neutrinos, and we studied the errors associated with this mixing. So how accurately we can study then these heavy neutrinos, and these are these ellipses that you can see here. This is for the scenario where the mixing is only 10%, and this is for the scenario where the mixing is equal to 1. So this is an interesting paper, and then what's nice is that we are performing this analysis together with a PhD student from Vanderbilt University and myself, experimental at CMS, and hopefully this paper will come out next year. The experimental results. Another very interesting idea is the production of Z-prime bosons through BBF, and we have similar claims. So before, only BBF, only Z-prime searches were produced or were considered, through Drell-Yan mechanisms. But the thing is that we don't know how these Z-prime couples. They could be preferential couples only to third generation, for example, and only to perhaps the color sector. If that happens, how do we study this? There could be scenarios with the Z-primes, for example, have preferential couplings to vector bosons. So in order to do this, so that we came up with an EFT, and we basically vary also the coupling of this prime using a kappa factor, and we perform the whole analysis for this prime particles using the Vector Boson Fusion case. So what we found was very interesting. The black curves, this is the cross-section as function of Z prime mass. The black curves represent basically the production through BBF, and the red curves represent the associated production with a standard Drell-Yan production mechanism. So this is for two different coupling scenarios here, where you consider basically a coupling scenario mainly to fermions. And what you see here is that the Drell-Yan, when you consider the coupling to fermions, so the Drell-Yan is has greater cross-section for the primes below 1500 GeV. After 1500 GeV, the story changes, right? So BBF is dominant. And these curves here represent the coupling, preferential couplings to vector bosons. And now, so it's backwards. For low masses, Vector Boson Fusion has higher cross-section with respect to Drell-Yan. So this analysis, as I mentioned, we're also doing it experimentally. We have people from, I call it with my colleagues from Vanderbilt and A&M, a very large analysis team at CMS. And we have people from Punjab University, PhD students from Vanderbilt that are working on this analysis. And we also expect to publish it next year. Okay, so we did the phenomenological analysis. Is again, what I've been talking about. So we came up with two different channels, final state with taus, final state with muons. And basically, we again show the signal significance as function of Z prime mass for different luminosities. It's basically the same concept. We show the feasibility of these searches experimentally. So we propose the model, we propose basically the methodology, and we show, what is the expected sensitivity under different luminosity scenarios. And so then we do, so since we also do experimental physics at CMS, so then we do the experimental analysis. Okay, let me switch to another very interesting idea, and it's the idea of anapole dark matter. And anapole dark matter is a very interesting concept. So in order to understand what anapole dark matter is, we need to recall the scalar and vector potentials from basic electromagnetism. If we perform a Taylor expansion, on the vector potential around, X prime, you will have, these higher order terms that are called anapole moments. And these anapole moments have been measured experimentally and are associated with toroidal magnetic fields and toroidal currents. So here you have this anapole moment. Okay, this is basic electrodynamics that you can review. Nevertheless, this has brought a very interesting idea. So one of the interesting class of dark matter models is where this dark matter particle is self-electrically neutral, but it couples to photons through higher multiple interactions. So this scenario has been considered in many models, actually. So in Technicolor, composed dark sectors, supersymmetry, simplified leptophobic models, and others. So the BBF then, the idea is that we can probe this type of scenario considering basically multiple moments associated also with vector boson fusion topology. So previous studies have considered the dark matter candidate to be a Majorana fermion, and you know that by definition, this means that it is a CPT self-conjugate particle. It has been proven that these massive Majorana fermions allow factors that are anapole moments, a higher order multiples of it. Then basically we have considered this model an EFT approach where we basically incorporated anapole interactions, effective interactions. Here we have the lambda, which is the cutoff scale, and we have the chi, which is basically the dark matter particle, and here is our standard electromagnetic tensor. So basically, this is the idea. We have our vector boson fusion process. We have the jets that basically radiate the W's. These W's fuse at a given point, produce an excited photon, and then this excited photon can decay to two dark matter particles. So what's very interesting and was very appealing of this paper that we published at PRD in 2019 is that we found that BBF anapole dark matter production cross-sections dominate over those more traditional monoset and monojet processes. So the red curves here shows you basically the production cross-section as function of the dark matter particle mass for the monoset process, considering a lambda equals 1 TeV, and the blue ones consider basically the anapole dark matter production considering different values of lambda. And you can see that the difference in cross-section is quite sizable, or even 2 orders of magnitude, making this analysis very appealing at the experimental level. And again, as you can imagine, we are also doing this analysis at CMS. We have people from the University of Kyungpoong in Korea, Vanderbilt University again, and myself. All right, so then the idea or something very interesting we found is that because this process is come mainly through WW fusion, so this is more like is more like a T channel rather than an S channel. The jets are more forward, so you can basically suppress heavily the backgrounds, and then the search has quite good sensitivity. So we again then place some bounds on the expected signal significance, taking into consideration lambda, the energy scale, as function of the dark matter particle mass. And here this dotted line shows the expected sensitivity for a 5 sigma discovery counter. We did this for 100 inverse femtobarns, and we did it also for a luminosity of 3000 inverse femtobarn, where we extend, a little bit. We go from 1100 GeV sensitivity to 1600 GeV roughly on lambda as function of the chi2 mass, and we can go from masses of 1 GeV, and we have sensitivity to probe more or less even up to 200 GeV on the dark matter particle mass. All right, this is the last idea. I will explain basically the last analysis, and with this I will conclude my talk. And is basically also we can probe heavy to spin. We can probe spin to heavy resonances or bosons decaying into 2 photons. So what is the idea behind this model? So new massive spin-2 particles are predicted in theoretical extensions of the standard model, attempting to solve the so-called hierarchy problem. Such theories are propose that gravity basically is diluted compared to other fundamental forces because it can propagate through additional dimensions. So we know the Randall syndrome models, and we know that they postulate the existence of these gravitons in these compactified dimensions. This theoretical model then several times include or predict massive spin-2 particles that I'm going to refer to as Y2 particles. these particles can be potentially detected, for example, at the LHC, and we have proposed a mechanism through vector boson fusion where these white 2 decay to 2 photons. Why 2 photons? It can couple to fermions and color parts to fermions, basically leptons and fermions and quarks, but we have decided to use the 2 photon signature because it's a super clean signature to detect this type of production that potentially have very low cross sections. Therefore, so we have considered the 2 photon final state as a golden signature, and we consider again an EFT model, basically where we have modified the Lagrangian, the standard model Lagrangian, including 3 different terms. The first term basically corresponds to the interactions of this Y2 particle with the standard model gauge fields. So here we have the gauge bosons and also the interactions with fermions, and we have this kappa B factor that allowed us to modify the coupling of these objects to the vector bosons and to the fermions. We also included a term that accounts for the interaction of these Y2 particles with the standard model Higgs, and we have also included some terms that include interactions with some non-ghost fields, the Fadeev Popov ghost fields into the theory. So we have yet again included performed the study of the significance as function of kappa, the coupling to the vector bosons, and also the coupling to the to fermions. And here you have the Y2 mass, and the gray area corresponds to the phase space where the unitarity in the theory is violated. So we did this for 100 inverse femtobarn and for 3000 inverse femtobarn. This paper was also published in PRD in 2019. All right, so I'll reach the end of my talk. Let me just say a few more words. These are my most important collaborators and mentors. So Professor Teruki Kamon from Texas A&M University, which basically adopted me. I got my PhD from Vanderbilt, but I basically did all my physics analysis at Texas A&M at the Mitchell Institute of Fundamental Physics, worked with Teruki and Alexei Safanov, two very well-regarded experimentalists, I will say now, I will dare to say even in the world. And then also now I work with Professor Alfredo Gurrola, who at the time where I graduated, he was not at Vanderbilt. And then we got a very similar common interest. Afterwards, we met. And then, so I worked very closely with him. And he also has become like perhaps, you know, one, if not my most important collaborator. And also Professor Carlos Avila from Universidad de los Andes in Bogota, who I regard him also as a mentor, a close collaborator, and a model to follow here for high energy physics, I'll say, in Latin America. So the summary of my talk is that the LHC is the most powerful particle accelerator ever built. There are several important discoveries that have been performed already. So we have the Higgs discovery, and we have several discoveries from the LHCb, and we have these very important B meson anomalies that could indicate presence of new physics also from LHCb. The physics programs at the LHC are just starting. We only have collected 5% of the total expected luminosity that we expect to collect during the LHC era. So we need to remain hopeful. We need to remain positive that new physics is going to come. Every time the discoveries have been more and more difficult. I'd like to remind you the top discovery, it took a long time, and when people was throwing out the towel is where the discovery hit, and we found the top in a mass range we never expected it. Okay, and BBF has shown to be a very powerful tool to explore uncharted territory at the LHC, not only in supersymmetry, but also on other extensions, exotic extensions of the standard models. I would say that we are living in very exciting times. Please stay tuned, because I believe that, and this is my personal belief, that greatest discoveries are yet to come. So thank you very much. And now we open time for some questions.
Thank you very much, Andres, for the fantastic talk. It's been very, very nice.
Thank you.
So let's start with the question. I have a couple, and I see that there's a couple of questions on the chat. But let's start with the audience here. I also believe there are a couple of students of yours. So hey, it's your chance to
to pay me back.
So I don't know if there's any question from the public right now. Okay, let me start. Okay, let me start. with the question I'm most interested in. So what are the expectations for the high luminosity LHC regarding a vector boson fusion? Because you will have to modify the cuts, right, due to the higher luminosity.
Higher pileup.
Yeah. Those things experimentalists have to deal with. So how do you expect the the production cross section of the process of interest will be affected by these cuts?
Yeah, I guess that we talk more than the production cross-section being affected. I will say that the acceptance of the analysis might be, affected up to some extent, because it is true that we're gonna have higher pileup once we go to the high luminosity era, but the detectors have been improved. Now we have a PLT, for example, on the pixel detector that monitors quite nicely, for example, the luminosity, and also will allow us to have a better handle, on secondary vertices. So the pixel detector is being upgraded, and now we're going to have tracking, including the triggering, including the tracking. And this will be huge, including the pixel detector. This will help us, lower significantly, the noise from pileup, having this capability. Also, the calorimeters and most of the technologies have been upgraded. We have learned a lot, and then that also will place a huge role. So although pileup will place, some role, I will say that the improvements will on the detectors and our software and our understanding of the detector is also going to help us diminish a lot of the impact we're going to get, from these processes. It's very hard, to give you an exact answer if our analyses are going to suffer, a hit on the acceptance that will limit, our possibility to probe some of these complicated areas, because this is we're yet trying to understand, these type of scenarios. In this last phenomenological paper on the Higgs, we took a more aggressive pileup scenario using Delphis. And then still we see that there is a great potential, to explore these regions where we don't have sensitivity. So it plays a role, but I say that we have other tools, we have better detectors, we will have more data, which is also important, and we have, people that is just scary smart working in this type of problems, so we can have a very good handle at new physics if it is there.
Right. Super. Thank you very much. So before I proceed with my other questions, let's see if somebody else here wants to ask something.
I have a question.
Yes.
Yeah.
So first of all, very nice the talk. I like it a lot, especially because since I work in the part of the dark matter side. So many of the studies that you presented, I was with the eyes very open, looking at the diagrams. So one question one is quite naive in the sense, which is kind of the minimum mass or maximum the mass range of the intermediate particle that more or less LHC would be sensitive, because there are some models that can push these particles to the TeV scales, and maybe it's hopeless to look in vector boson, even though they are very interactive with the vector bosons. With the W. But this is the first question. And the second question, a little bit related with this. For instance, in the case of the type 2 CISO, you have there is a scalar that is a triplet. So is this also have been analyzed? Because usually when you put a Higgs, it's a doublet, so it's less, the strength with the coupling with the W is less strong. So I don't know if this is a possibility that have been studied.
Okay, then in order to go to your first question, it's interesting, very interesting, because with BBF, if we talk purely about BBF, so what we've been showing is that it seems, depending on the model, we'll be able to probe certain scenarios, as you can see it here, masses that go, from 1 GeV all the way to, 1 TeV. roughly speaking, right? It depends. This relies on the model. So BBF, it's very nice to go to the lower mass sector, you know, for these dark matter particles, because, you know, of the characteristics of the process. Of course, if we go to do a more like a high mass search, you know, for even resonances or even dark matter, so Drell-Yan, you know, might win, you know, after some masses. But the advantage of VBF is that precisely allows you, because you can reduce backgrounds dramatically with respect to Drell-Yan, it allows you to probe, you know, smaller masses. And this is very appealing because we really don't know what the dark matter mass is. And then some theories said that it could be very, very, you know, low mass. So here what we can do is 1 GeV. We cannot go below 1 GeV. But another interesting aspect, and I want to emphasize, is that it also allows you to probe, BBF allows you to probe the couplings, right, of this dark matter particle and go to scenarios with it only couples to the weak sector and is more like color phobic. Now for the LHC, you know, as a general, just to answer, you know, I broke your question into parts. Just in general, of course, we are constrained. We have 13 TeV center of mass energy, so the protons are conformed, you know, formed by 3 quarks. So we have 6.5 TeV per being, so we have to break the energy in 3. So at the center of mass, at the maximum, you can probe masses of like roughly 5 TeV. We cannot go beyond that, right? If we can increase the luminosity to the design ones, you know, 14 TeV, we will get a little bit more to go to the very high sector, even to probe, you know, I don't think that nobody expects the dark matter to be 5 TeV, but to probe perhaps, you know, at least these heavy Z-prime resonances and so on and so forth. For the other question on heavy neutrinos, so we follow a more like a EFT approach. We've also used this left-right model, but, and then you got me on that question, I need to review yet again the paper. This was a paper back in 2017. And I need to recall, you know, if we consider, you know, the third type seesaw mechanism, I believe we did, because at the time, you know, the type 1 and type 2 started being more like a rule out, you know, in several experiments. But I don't have the defined answer, so I don't want to give you like a whatever answer. It's just, this is a theoretical detail that, you know, this was published in Physics Letters B in 2018. So yeah, I have to look those details.
Okay, thank you.
Sure.
Great. Okay, so let me go to the questions on the chat. We have more questions now. The first one is about the Y particle. Is that the dark photon maybe on the?
No. The Y particle, I believe, is the spin 2 resonance. Yes, right. Here, spin 2 boson, the Y2. Yeah.
Right. Exactly. So they are asking how long does so what's the lifetime of this particle?
Yeah, I mean, that's a good question. So we consider to decay very promptly, right? Such that it decays, you know, right, basically, once it's produced, it's almost decays very promptly. So that basically we can have the 2 photons to be detected within the detector volume. So this is the constraint, of course, because you want to detect 2 photons, you know, within the calorimeters. So yeah, this was the consideration.
Great. Okay, super. So it's a prompt particle. That was a question from Werewolf, who says, nice work. There's another question from Federico von der Fallen. So he's asking, in the search for Higgsinos in Vector Boson Fusion, would including a relatively soft tau in the final state be feasible or worth the additional work?
Yes, I mean, it's interesting because that's exactly what we did. So we consider, actually, we didn't go to the tau only. So we were more agnostic in terms of like democratic in the possible decay products. So we had to be democratic because these are Higgsinos. And basically we consider final state. So we initially consider final state with single electrons and single muons, and with 2 electrons and 2 muons, because those were the most sensitive ones. Once you go to taus, and you know, I always like to make my life difficult because I always have worked with taus. Taus are quite complicated. So once you go to taus, so the problem is that you lose a lot of sensitivity because the minimum PT is 20 GeV, while for muons you can go as you know, as low as 5 GeV, and for electrons 8 GeV. And then for taus, the problem, you know, once you consider this, is that you lose a lot of sensitivity. It might be feasible, right? We didn't study it because you know, it's a lot of work. But we did it initially with electrons and muons. But it is an analysis that we had in mind, you know, and could be an interesting phenomenological paper. But out of the selections we use, we might require actual additional, some kind of key selection to reduce more backgrounds. So we are considering definitely for the latest search for the Wino-Vino interpretation that is going to come up. Actually going to give you the heads up. Now we have a multi-lepton huge search where we're going to have signatures with 1 lepton, 2 leptons, 3 leptons, missing ET, and we're going to probe supersymmetry for Higgsino, Vino, Wino, and also anapole dark matter. So this is going to be a huge search. We have a tremendous amount of work done at CMS, and we have, I think this is one of the best teams I'm working with, because I have like a scary smart PhD students working on this analysis, but scary smart. So then hopefully this analysis that is quite broad and, you know, is quite you know, ambitious, we expect it to be published, not lying, you know, if things go well, by the end of next year or beginning of 2022, because it's quite ambitious. But then, there, just to finalize my answer, so we're also taking different approaches with compressed taus. So we're also going to consider the compressed tau scenario. Yeah.
So what is the luminosity that you will be analyzing on that search?
So run 2. We're in the approval process for run 2 luminosity. So basically we're analyzing 139 inverse femtobarns with the full, you know, all with many channels. And as I said, it's going to be a very ambitious paper.
Super.
Yeah.
Very nice, very nice.
So we,
so
actually
we need to hurry up before you rule us out.
Yeah, you better publish before we rule. No, we'll see. I mean, I you never know, right? You never know if we might find something. So we haven't unblinded the data, so I cannot tell you anything because hope to go to the pre-approval before the end of the year, and after the pre-approval, we're allowed to unblind, and then we will know. But I won't tell you until the paper comes out.
Great. Let's see. There's okay. So Federico says thanks. There's another question from Daniel Ocampo. Let me. Okay. So the question is if this distribution for BBF processes, this is the distribution of jets. The distribution of HT, all of the things. So could they change in other models and get closer to the standard model distributions?
Yeah. No, I mean, generally for BBF, the thing is that once in BBF, you basically have your quarks radiating the vector bosons, and these vector bosons fuse, right? That's the whole idea. Let me put a diagram. Here I had a diagram just to answer this. No, it was to answer this question. This one. So you have then your partons, you know, radiating the W's or the sets, and then they fuse. But the problem is that if you require these neutralinos and charginos to be heavier, you will need more energy here. And if you need more energy, these jets have to be more energetic. So which means they should be more, you know, higher momentum, should be more forward in order to balance out, you know, the central energy you require here. So so there is a correlation between basically the masses, right, of the supersymmetric electroweak equinox, and the jets. And this, of course, could change slightly bit the topology. What I, for example, showed for the non-SUSY scenarios here, for example. No, let me use this one, the anapole dark matter one. In the anapole dark matter, I mentioned this comes basically from WW fusion, right? This is different with respect to the previous diagram I showed from supersymmetry, where in that diagram that was more the Vino-Wino approach, it could come more from an S channel rather than a T channel, right? The change in the topology, actually, when this comes from WW, makes these two jets to be quite energetic, and then what ended up happening is that the jets are even more back to back. So then the back-to-backness, let me put it this way in broken English, is related with how energetic is the process in the central part and what is the dominant, production mechanism. Now, you can consider, other scenarios that are not BBF. You can have searches, that are inclusive and consider two jets that could come from ISR. And then you can look at the topology, but the topology of these events will be more like this of the background. The jets are going to be dominantly central, because these BBF processes, once you require the jets to be in opposite hemispheres, so it gives you this distinctive feature. So then the topology of the analysis changes completely, and of course the background composition changes, and you have a complete different analysis. So it's not the same to look for new physics considering two jets, just two jets, than considering two jets with the BBF topology. Everything changes. Okay, so I hope to have answered the question.
Great, I think you did. so fantastic. Thank you very much. Federico says that I have to publish before they discover something, but Federico should publish too.
If we discover something, I think that I'm gonna go to Antioquia and get drunk with my Antioquia colleagues.
Oh yes, and we will all join you. We will all join you.
And I have to mention the 13 TV paper. The Missinity channel BBF. It was led by Jose Ruiz, a professor from Antioquia, and I keep working with Jose. Jose is working with me on BBF Z prime, on the Drell-Yan Z prime. We also have a Drell-Yan Z prime. He's also working with me. He's helping us, on the BBF, the latest BBF SUSY. He's an expert on signal production, Monte Carlo and stuff. And yeah, he's one of my closest collaborators also. So big thanks to Jose for all of his work.
Yeah, we will have him as a speaker soon.
Okay, good.
For sure.
Let me know. I will connect and ask tough questions.
Totally.
No, I'm just teasing.
So let's see. No, there are no more questions on the chat. Maybe somebody has.
I have one very
there you go, Roberto.
Another very naive question. In the
yes.
sense, when you make this analysis, is it included in the BBF scenario the possibility to produce same charge leptons?
Yes.
So two positive muons or two.
Correct. So since the ATV analysis, Roberto, so we consider the final states, for example, two muons with opposite sign or two muons with same sign, two taus with opposite sign, two taus with same sign. So we had 8 channels at the time. For the single lepton scenario, of course, you don't require any charge. So it could be positive or negative. But yes, so this, and basically, actually, and this is an excellent point, and thanks for reminding me, the same sign leptons are the most sensitive ones. In the dilepton searches, the same sign is the most sensitive ones. Most of the sensitivity from dilepton searches of BBF comes from same sign. Why? Because backgrounds go down, and by BBF topology kills, QCD and other backgrounds. So it's a very, very clean search. So this is a very important part of the analysis. In the case of Z prime, it's different because since the leptons come from Z prime, so they must be oppositely charged. So then you use that characteristic in order to lower, to diminish contribution from other processes, where you can, or from QCD and other processes that could have, charge blind topologies.
Okay, thanks.
And I mean, in that case, if you have two same sign electrons, that could also, this kind of operator that leads to this process could also give contributions to neutrinoless double beta decay. So I don't know if you're aware of how the constraints from this kind of searches compare to the constraints coming from neutrinoless.
No, you kill me. No, I don't.
Sorry.
No,
This is
no,
a typical thing
that's
you
quite
do when
interesting. That's
heavy
interesting,
neutrinos.
actually. That's very interesting, Joel. So yeah, actually, you got me something to think about. There is a little paper I've been trying to work with Verna. I have a hard time pronouncing his last name. Rodejohan. Yeah, thank you.
Yes.
You know him from Heidelberg. And we have a little paper on the production of majorons, basically using BBF, and we have calculated several cross sections with a super bright master's student that we had. Actually, you know, I was the main advisor. He got his master's over there, but I directed most of the work, and you know, Verna acted as a co-advisor, but the student is from Heidelberg. And we're trying to come up with solutions because the majorons now have to be, you know, lighter than we were hoping for, and then it's going to be harder to detect. But we're trying to probe this type of heavy neutrino processes, and yeah. So perhaps we can use some of your input. Yeah, I put it on hold because right now I'm too busy, and like we've been working actively until like 2 months ago, and now the semester is killing me. Then yeah, but that's a little paper we're trying to come up with production of majorons with BBF. Yes.
Okay, so just to conclude, there's one final question from the chat from William Torres Bobadilla, asking if you can say anything about N4LO.
N4LO.
I guess it's next leading order.
Yeah, that is a lot of work that the theorists need to do. Need to make. Yeah, so far what we do basically, we many times in SUSY, you know how complicated it is go to next to lead in order. Sometimes we can do it for some processes and then derive, you know, just some K factors to correct the cross sections. But most of our cross sections are purely math graph lead in order. Because the next to lead in order, or next to lead in order, those are like, I think that there is a lot of theoretical processes going on, work going on the area. But yeah, so far we've been using it just like, in some cases, some analysis, we can use some K factors, you know, that can change the cross section up to 30% to the, you know, next to lead in order, but never have tried, you know, next to lead in order. For the models we have, we don't have that, unfortunately. Yeah.
Okay, great. So that's it. I think we can wrap it up. Awesome. I don't know if there's any urgent question from the audience right here. 5, 4, 3, 2, 1. Okay, no. Great. So thank you very much, Andres. It's been fantastic having you. It's been a great talk as always.
Thank you.
And I'd like to remind everyone that we have a talk by Hector Silva. It should be in 2 weeks, if I'm not mistaken. So please stay tuned.
Thank you very much.
So thanks, everybody, and see you next time.
Bye-bye.